Hello, my dear students. Today we are going to discuss about electronic, especially exceptional electronic configurations in the periodic table. You see, generally many times this particular question comes in various competitive examinations. Already we have seen some in some competitive examinations electronic configurations are asked, like electronic configuration of gadolinium, FBlock element, DBlock element, like that. Because in S and P block elements, there is no element with exceptional electronic configuration. Only this exceptional electronic configuration comes in case of D and F block elements. So let's start about exceptional electronic configurations. Exceptional electronic configurations. Actually in NCERT we are mentioned exceptional electronic configurations, but in different chapters. In structure of atom, chromium and copper are highlighted. D and F block elements, some elements, okay, in chapter wise exceptional electronic configurations are given, but anyway in a single page we have to discuss the elements with exceptional electronic configurations. So first let me talk about D block elements. In D block elements, some elements show exceptional electronic configurations. What are these elements? We know chromium from 3D series show exceptional configuration, and the group member of the same group, chromium group. Molybdenum also shows similar properties, and in vanadium group, niobium shows exceptional electronic configuration. Iron group, ruthenium. Cobalt group, rhodium. Let's talk about nickel group, nickel, palladium, platinum. Some anomalous configurations are there, and copper already exceptional configuration is there. In the same group, silver and gold also show exceptional configurations. So these are the elements of D block. We know these are transition elements with some exceptional electronic configurations. So let me start with the niobium. Vanadium group. Actually in vanadium we know NS2 and NS1 D3 configuration is there, but in this NS1, that is 5S1, 4D4 configuration is there. One electron migrates from this to this one. Vanadium atomic number is 23, to 23 plus 18, what is its atomic number? 41. Because in transition elements the atomic number difference between 3D and 4D series is 18, 4D and 5D is 32. Okay, so 23 plus 18, 41. This is before F block elements. So krypton atomic number 36. When you are going for any competitive examination, it is mandatory to memorize atomic numbers of all noble gases, because already I have made a video on group number and period number. In that also the atomic number of this particular noble gases is very important. So now let me teach this chromium and molybdenum. In chromium, post-argon configuration, we know 24 atomic number, 4s1, 3d5. Actually, it should be 3d4, 4s2. After filling of 4s, electron enters 3d. But we know exactly half-filled configuration and exactly completely filled configurations are more stable configurations. So for getting stability, electron migrates from 4s to 3d. That does not require any high energy because of very small energy difference between 4s and 3d. Well, molybdenum, below this molybdenum is there, atomic number is 42. Post krypton, 5s1, 4d5 configuration. Okay, 5s1, 4d, 3d, 4s, next period 4d, 5s. One principal quantum number value increases. So molybdenum is over. Ruthenium and osmium also have some exceptional configurations. Ruthenium in iron group shows exceptional configuration. That is D7, 4D7, 5s1. Rhodium shows exceptional configuration. That is 4D8, 5s1. One electron jumps from 5s to 3d, no, 4d. Okay, and palladium platinum. Actually, nickel does not show any kind of exceptional configuration. Palladium platinum show exceptional configurations. Palladium is the element in which total S0 is there, but 4d10 is there exactly completely filled. But in platinum, 2 electrons migration is somewhat difficult because of high effective nuclear charge. So here we can say it is 6s1 and 5d 9 configuration, but you already know that atomic numbers. You see nickel 28 plus 18 46 plus 32 78 means, you know, after 4f series, after lanthanoids, platinum comes. So you have also to write 4f 14. That is completely filled, in fact, but that is post noble gas configuration. We must not ignore this. The post xenon 54 na 54 plus 14 68 plus 10 78 electrons are there. Exceptional configuration, but here no problem because 46 is before lanthanoids, before F block element. So post noble gas configuration, there is no F configuration. Okay, F subshell. And let's talk about the straight away NCERT example along with chromium. Copper is clearly mentioned in structure of atom. The copper post argon 3d10 4s1 configuration is there. We know it has exactly completely filled configuration that is very stable. In fact, 29 atomic number, 29 plus 18 48 no 47 plus 32 79. Otherwise, the next to platinum, gold is already there. So here 47 post krypton, that is 36 plus how many electrons? 11 electrons. So that is again as usual the same group. Xenon 54 are there, 54 4f14 is filled. Okay, 54 plus 14 already 68 are over. 68 plus 11 will give 79. That is clear. Very simple logic. So in copper group, all the elements have completely filled D configuration, that is D10. So you can easily memorize. Chromium and molybdenum belong to same group. Copper, silver, gold belong to same group. Palladium, platinum belong to same group. So these 7 elements you can memorize easily. So only you have to memorize, only you have to focus more on niobium, ruthenium and rhodium. Okay, the other members of their groups do not show any kind of exceptional electronic configuration. And you know, from class 11, even every student of class 11 knows that chromium and copper shows exceptional electronic configurations. So from chromium you can easily memorize molybdenum, and copper easily memorize silver and gold because they belong to same group. Palladium, platinum can be memorized. Okay, so what I want to tell you, before going to any competitive examination, if you know exceptional electronic configurations of D and F block elements in a single page, if you write all of these in a single page, then before going to examination, just go for 10 minutes, maximum 10 minutes you spend, and you will, if any question comes, then you will get 4 marks easily. Okay, no need to search various books, various chapters and etc. All exceptional electronic configurations in one single page. Now let us discuss about F block elements. You know, F block elements are also called inner transition elements. What? Inner transition elements. All these belong to group 3. Post lanthanum, these lanthanoids are there, 4F series elements. Post actinium, actinoids are there, 5F series elements. So in 4F series elements, what are the exceptional cases? Actually lanthanum and actinium, although they are D block elements, in general we study along with lanthanoids. Okay, because of their resemblance of properties with lanthanoids and actinoids. Okay, so we know atomic number is 57, it is 89. We know as per Aufbau principle, I mean Moyle's diagram, we know electron entry takes place in various orbitals in the increasing order of their energies. So after completion of 6s, electron must enter 4f. Okay, no doubt in that, because 5d has more energy than 4f. But lanthanum and actinium are exceptional cases. In these two, electron enters d before going n-2f, electron enters n-1d. So no doubt these are also exceptional cases. Okay, so post xenon you can write. Post radon. Radon is 86, na? 86 plus 3, 89. 54 plus 3, 57. And after that, is there any exceptional configuration, sir? Cerium has exceptional configuration in this 4f series, that is post xenon. It has 4f1, 5d1, 6s2, although it is an FBlock element, but still one electron is present in 5d. And after this, next gadolinium, its atomic number is 64, 58. When it is 64, when you can progressively fill electrons in f subshell, and here 4f7, 6s2 is there. In addition to this, in 5d, again, I mean, in fact, final electron is present in 5d, if you look at this. Okay, but FBlock element. So what is the reason for this? Exactly half-filled configuration. 4f7, f subshell has 7 degenerate orbitals. So 7 orbitals have 7 electrons, symmetrical configuration. Exactly half-filled, stable configuration. And finally, you see lutetium is there. The atomic number you all know very well, that is 71 in fact. 4f14, 6s2, 5d1 is there. Again 5d1. Before lutetium, ytterbium is there. That has 4f14, 6s2 configuration, but the 4f14 is retained in lutetium just like gadolinium, because stability is the reason. Exactly half filled here, exactly completely filled here, and there is no other reason. Before gadolinium, europium is there. Here actually europium is there, here ytterbium is there. It has 4f7, it has 4f14. Same stable configuration is retained in next elements. Okay, so actinium. Next we have thorium. Its atomic number is 90. The exceptional element, because an FBlock element without having any f electron. Okay, so it is 6d2, 7s2, post radon configuration. Quite exceptional. No electron in f subshell. And protactinium, uranium, neptunium. So after thorium, in 3 elements, again some discrepancies are there, like 5f2, 6d1, 5f3, 6d1. Okay, in d, 1 electron is present. That is the only case. It is 7s2. Okay. So 4f2, 5f2, f3, f4, but d electron is also present in addition to f. So these are exceptionals. And just below gadolinium in 5f series, curium is there. It has 5f7, 6d1, 7s2, exactly half filled. And at last, in the final, lawrencium, again completely filled configuration. For getting stability, this 5f14 is retained in lawrencium. Actually, before gadolinium, europium, before lutetium, ytterbium are there. They have their usual configuration. Europium and ytterbium do not have any exceptional configuration. But post europium, that is gadolinium, and post ytterbium, that is lutetium, have exceptional configurations. Before curium, no exceptional configuration. Before lawrencium, that is nobelium, no exceptional configuration. Only exceptional configurations are there in these elements of total inner transition elements. So actually we have to more and more focus on exceptional, exactly half filled and exactly completely filled configurations, because questions are frequently coming from stable configurations. Okay, let us solve 2 to 3 questions from previous competitive examinations related to exceptional electronic configuration. Now you see all exceptional configurations in a single page. 10 minutes is sufficient to study all these. Well, let's see examples. I'm going to take some examples from previous competitive examinations. So we are asked the electronic configuration of cerium plus 3, gadolinium plus 2, gadolinium plus 3, like that. Okay, these are already asked questions in national competitive examinations. So cerium you know very well, cerium configuration, but you see some topics in chemistry to be memorized, no doubt. 100% conceptual questions may not come. Okay, even in JEE paper or NEET paper, you see national level examinations, some memory based concepts, memory based questions are also coming. So it does not mean that everything you have to memorize, because when we are asked the configuration of any element or ion, along with this we are providing, we are giving some information like their atomic numbers. Okay, from the examination side, atomic numbers are given. So when we are given atomic number, cerium atomic number, gadolinium atomic number, like that europium, any atomic number, so you can easily understand, you can easily write, because before cerium we know xenon is there, xenon 54 is there. Cerium atomic number is given 58. This is given in the question paper. So 54 plus 4 electrons means what? You see 6s2 is there, exceptional configuration. Cerium has exceptional configuration, that is 4f1, 5d1 is there. So now you have to remove 3 electrons. From where? Always you see electron removal must be from the valence shell, outermost orbit. So this is the outermost orbit, remove 2 electrons, and you have to remove 1 more electron, then you come to penultimate shell. This is penultimate shell, and from anti-penultimate shell we must not remove the electron. If we are given cerium plus 4, then you go for this. So always electron removal takes place from outermost orbit to penultimate shell to pre-penultimate shell. Like you are given gadolinium plus 3, gadolinium atomic number you are given 64 in the question paper. Then you know xenon has 54 atomic number. So 54 electrons are already over. So now you go for gadolinium. You know gadolinium has an exceptional configuration. 6s2 is there, 4f7, 5d1. You see 54 plus 10, 64, yes. 64 atomic number, 64 electrons are there. Now I want to write gadolinium plus 3 configuration, then remove electron from outermost orbit. In outermost orbit we have 2 electrons, remove these 2 electrons, then you go for penultimate shell, well sir, 0, so 2 plus 1, 3 electrons I have removed. So 4f7 configuration is left, that is stable configuration. That's why gadolinium often forms GD plus 3 or GD plus 2. GD plus 4 is not possible. Already after removal of 3 electrons, effective nuclear charge increases, and moreover stable configuration is also there. 4th electron removal is very, very difficult in gadolinium plus 3. Like that you can also write gadolinium plus 2. So when we are given any question in examination related to configuration or exceptional electronic configuration, any question comes, along with the question that particular atomic number is also given. So for this you don't need to worry. Okay, so thank you for watching my video.